Thank you. Thank you for joining this last session of the whole conference. And I have the pleasure to kick it off with my topic. So as introduced, I'm going to talk about oxide dispersion strength materials. In this case, since we are in the session for steels, we're talking about steels. I'm from the University of Wuppertal. I spent lots of my research years also at the Fraunhofer IIT in Aachen. So most of the results are actually done in Aachen. So thanks to the IIT in advance that I'm allowed to use this data. And also thanks to my co-authors, Splitting Aus and my supervisor, Professor Bridger. So a short outline of my talk. We will have a short motivation. So why do we deal with this kind of material? Why should we consider additive manufacturing with this kind of material class? We will have a look also at the powder manufacturing, because for a composite material, you typically need to do some work before you can go printing. So we heard about this yesterday already, a composite of 316L and silicon carbide. So there was also ball milling performed. So here it's kind of like the same. And we will actually also have a look at the nanoparticles, because this is a nanoparticle reinforced material. We'll have a look at the dispersion and also the chemistry. Very briefly, in the end, if there's some time spare left, we can also have a look at short on mechanical properties and the conclusions. So as it is a comparative study, you can already judge from these pictures that we're going to compare some different processes. So we have the LDD, so the direct energy deposition. We have which is called the high-speed laser cladding. So this is kind of like the high-speed variant of this process. And of course, the well-known laser powder bed fusion. So first, a short motivation. So I think most of you are kind of familiar with this concept of oxide dispersion strength. If not, it's rather simple. So you have a metallic matrix and you disperse nanoscale oxide particles, and that's basically the concept. You can do this with basically every metallic material. So there are also works from MPA, did this with nickel-based materials or intermetallic materials. But let's stick to steels here, and typically you will find some stainless steels which are used as a matrix alloy. So we're not going into these very high-strength steels, because when we add nanoscale oxide particles, we will receive some dispersion and strengthening. So we can actually make our stainless steel a lot harder. Okay, so what is it used for? So why should we even consider these materials? Actually, this class of material was originally developed for nuclear power plants. So I brought here a picture. This is obviously not a power plant. This is like the assembly of the heat rods, which are used in nuclear power plants. And this is why are they used there? Because they have a relatively high resistance to high energy neutron radiation. So if you add these oxides and disperse them right freely in your matrix, you will provide some sinks or recombination sites for defects which are induced by the radiation of the neutrons. So this is basically the idea why these materials were actually planned for nuclear power plants. So now we in Germany, we are not a big fan of the conventional fission nuclear power plants, so we're going to switch them off in a few months. So maybe we will look more into more advanced reactors in the future. I think every one of you have seen such a picture here, or one of these. This is obviously a photomontage, so it's not a real picture, but of course we're talking about fusion processes. Yeah? So this might be the next generation energy production for the whole society. So there were some recent advances in the US, so it's I hope we are pretty close to get this thing going. But this kind of material, it certainly does have some sort of a W. So you can, of course, look at the radiation tolerance, but this is obviously only interesting for very special applications. If you have a look at other applications, these materials are also famous for extremely high creep resistance. Yeah, so, and as a mechanical engineer or materials engineer, you directly know where is this important, of course, in combustion engines. So whether it's for propulsion or it's for energy generation in a gas turbine, it's always interesting also to use these materials, and they are actually considered for use in these types of engines. So now we're going to talk a bit about why should we consider it for AM. I mean, there is a, let's say, conventional manufacturing route, so you can manufacture these materials. So why should we do this with AM? So why is it important? So in the first step, of course, we have this mechanical alloying. We need to form some sort of a homogeneous powder composite. You have to do this consolidation, which is typically done by sintering processes. Okay, there are also some more advanced sintering processes like SPS nowadays, but these are the conventional ones. And afterwards, you have a relatively, let's say, not very complex part, and you can do some subtractive manufacturing and design your part out of this material. So obviously, this production chain is quite long, and with additive manufacturing, we have the chance to shorten this quite significantly. We know from literature that we can produce composite materials with additive manufacturing due to high solidification rates, high cooling rates, and small melt pools. So why should it not be possible with this kind of material? And moreover, we can also combine the consolidation step here and also the shaping. So the final part, we can produce it like directly near net shape for the final product. Okay, so there are two very attractive advantages which additive manufacturing could bring to this alloy class. Of course, in the end, this is kind of like the standard argument for every additive manufacturing. We can produce parts with very high complexity, so much more than we can do with subtractive manufacturing in many cases. So if we are at this point, so which additive manufacturing technology should be used? So obviously I was at the Laser Institute, so I kind of had to narrow myself down to laser processes. So I'm not talking about electron beam processes or others, but still, which one is the best? So in terms of mechanical properties, in terms of dispersion of my oxide particles. So if you have a look at literature, they will always say like, okay, cooling rate. This is the most important factor for this. So you need high cooling rates in order to freeze your oxide particles in your metallic matrix. You want to prevent them from agglomerating or from going to the top because of their lower density. So cooling rate is the key. Okay, so then we have a look. We did some calculations here from with FEM modeling to kind of simulate the cooling rate of these processes. We also used the process parameter for this steel. What steel I'm using, I think it's 2 slides, and we can talk about the steel. So just as an average, as a rule of thumb, so we have like here this cooling rate, which is relatively low compared to the LPBF one. This is certainly, of course, has something to do with beam diameter we're using. So this is much smaller. So we're talking here about 80 to 100 microns. Here we're talking about 600 to 1000 microns, just as a rule of thumb. And the high-speed laser cleaning is somewhere in the middle. So here we have some, it's like very green here. So I'd say like something to the power of 5. Yeah, so just as a rule of thumb. So from this relatively easy consideration, you can even already say like, okay, we think this should be the best one. So, but okay, let's try this. But before we can go printing, as I said before, we need to form a powder composite. So we need to disperse our oxide in our powder material. Otherwise, we will not get a homogeneous distribution in our final part. There are also studies from France who already showed that we really need that step. And this is the most basic process for doing that, mechanical alloying. We have heard yesterday from the colleagues from Liège already about mechanical alloying. And what we did here is we took our steel, so this gas atomized powder material, this had this composition. We have a fairly amount of aluminum, about 5%, and some titanium, 0.5, not that much. And we added yttrium oxide, 0.5 weight percent. I'm afraid it's not staying here, but keep in mind 0.5 weight percent is about that we are adding. Why yttrium oxide? It's said to be one of the most stable oxides. So just from thermodynamic considerations, and this is also the most researched oxide which is used in additive in oxide dispersion strength steels. So you do the mechanical alloying and you get some powder which looks a little like this. I call it like gravel-like structures. But we heard already this morning from Professor Niendorf that you can also use non-spherical powder for additive manufacturing. It works. So it's not that nice process. Of course, we always want our very perfect spherical particles, but you can use them. Of course, your flowability, it will go a bit down, but it's fine. We at our institute, we also thought about another process to get a powder composite, which is a bit more advanced, you might say, and we call it pH-controlled adsorption. So what we basically do is we throw our powders into water. So everyone will say, like, how can you dare and throw this into water? So, okay, in this case, we have stainless steel, so it's very, very good protected. So there are no reactions with the water. And the idea is if you change the pH value of the water, just say by adding a base, let's say sodium hydroxide, you can actually come into a regime where the surface charge of the steel particle and the surface charge of the nanoparticles are oppositely charged. So actually, these little nanoparticles are attracted to go to the surface of your metallic particles. If you then remove the water just by drying in the furnace, then you can get a powder material. So you have no force, which was impacted on the particles. So it's still perfectly spherical. And you have very nicely distributed the oxides on the surface, and you can use this for printing. So let's go to printing now. Okay, so we produce some larger structures. Of course, we started with the smaller structures and performed the DOE and to get a really nice process parameter set. I think you're all more or less familiar with this process, so I'm not going into detail. So this is just the large samples, how they look like. So we extracted some mechanical samples from these parts. So here just from some basic approach, you go to your microscopy lab and then you have a look at the structure. So we heard a lot about texture this morning in the planetary session. So we see here also that we have a very strong texture in our DED material. We also have the structure here, so a bit more high magnification. We also see here grains which are epitextually grown over the melt boundaries, so they're completely going through your complete material. And this is also kind of familiar with the regularly see the columnar grain structure from LTBF. So this is so far pretty standard, so everything what we can expect. We can go to more advanced microstructure analysis. Unfortunately, I cannot show it for the high-speed laser cladding since this is still on the way, so I'm sorry for that. But for the DED material, we see since we have, despite we have this very common grain structure, we see that we also have, like on a very lower scale, we see some of equi-X, so more or less equi-X grains. And if we zoom in more, we can even see a substructure here. I hope you can see it from the different grayscales here. And if you zoom in more, then you actually can even find some particles here. Some of these oxide particles we're added. The question is now, do these oxide particles affect our microstructure evolution? And the answer is yes. So basically, if you have here, look at the inverse pole figures from the EBSD measurements, you see on the left-hand side, which is designated here as raw, is like the Rufus material without adding any oxides. You see rather large grains here, and you also see some sort of texture in the building direction, which is up and down here. And if you have a look at the corresponding ODS material, you see that we have some severe grain refining here. Since Ms. Pollock was talking about misorientation, I quickly added this image also to my talk. So we see that we also have some really high misorientation between grain boundaries between individual grains. But since it's not a nickel-based alloy, so we don't have the problem of cracking in this area. So at least we didn't observe this in this studies. So we also did some XRD and had a look at some texture here, and saw that we actually have a stronger texture even after addition of oxide nanoparticles. To be honest, we are not sure really where this comes from. So you see, there's still a lot to do for us to see how we can proceed with this. If you have just, it's the same methodology we used here for the LPBF. So we have a much finer grain than in the LDD. We see also this grayscaling, so the subgrain boundaries here. So it's kind of like the same what we also saw in the LDD part. And of course, you also see here, it's not that well visible, but you see those little black structures here, which are actually oxide particles. So in the end, you can say, okay, this is pretty standard. We would expect that we have higher cooling rates, then we have a finer grain. This makes sense. If you have a look here also on the texture, it's rather the same. So here we don't see that much of a difference. It's a little bit hard to see it from here, but we actually have also here grain refining by oxide particles. Having a look at the microstructure, now we're looking now at the oxide particles, which are the most interesting one. Oh, I see it. To accelerate a lot. Okay. So you see here the nanoparticles. So from judging from these pictures, you can always say like, fine, it works. So we can disperse the oxide nanoparticles, which appear here as white spots. These are etched SEM images. So it works, it's nice. If you do now some calculations and some statistics and see how large are these particles here, you see a big difference. So actually we want to be in this range. We want to have the nanoparticles as small as possible. So in this case, LPBF should be very fine. If you have now a look, really trying to accelerate now, at the chemical composition, we see that we have aluminum, which is also in the alloy, if you remember the composition. We have also found some silicon. Yeah, we might ask where this come from. Silicon stems from the powder, it's a common contamination in steels. But since when we did like some APT measurements, we were a bit shocked that we were not able to find any oxides. So this is just one example. We examined multiple tips and we just found titanium carbides. So if you have a look here at the proximum diagrams. So we were quite a bit surprised since we obviously found them here, and why didn't we find them here? So we think this is basically the answer. So we had a look at the particle spacing, so the distance between the particles in your matrix, and this was quite high, so much larger than the size of one tip. So I guess we were just a little bit unlucky here and didn't find it. So in the LPBF specimen, we were a bit more lucky, and of course this interparticle spacing is a little bit lower. So we find actually particles. The chemical composition is rather the same. Here we even had the chance to kind of like do some TM measurements and determine the structure. So this is a YAG phase. So basically what's the crystal inside your solid state lasers. And we also find here some titanium carbides, and they look very strangely. So they're not like single carbides which are dispersed in your matrix. So we think here maybe this is not correct. So this is just an idea. We see here some dislocations where these carbides are sitting on, and so we can actually observe here some dislocation interaction with our oxide particles. So which is actually exactly what we're looking for. Okay, for the sake of time, just two more words to the mechanical properties. We performed some compression tests at room temperature and high temperature, so 600 degrees is our high temperature measurements, and we do see a effect of the oxides, in particular in the high temperature region, and the LPBF also have a higher strength than the DED part materials. So from this point, we would say like the LPBF materials are superior to the LDD. But basically, you can manufacture oxide dispersed materials from both materials. It depends a lot on your parameters, on how you set in your process. And we have pronounced grain refining, since this is a topic which is long debated in the literature, whether these oxides contribute to grain refining, yes or no. And that's, I think, I want to end my talk. Matter of time. Thank you for your attention. Sorry for the acceleration.